Thank you, Will and Miguel, and good afternoon. I'm here with my thesis partner, Addison to present to you our thesis titled Mechanical Performance of Stiffened Aluminum Panels as a Function of Weld Parameter Predicted via Finite Element Analysis. This was done under the advisement of Professor McMahon. Before I begin, I believe some acknowledgments are in order. First, we would like to thank Professor McMahon, our advisor, for his help and active participation throughout our thesis. Next, our reader, Dean Warner, and editor, Professor Lutz, for their feedback on all of our thesis submissions. Special thanks goes out to Metal Shark for making this thesis possible with their donation of the 6 stiffened aluminum panels. And last but not least, we would like to thank Professor Royce and Professor Mills for their expertise and guidance. In today's presentation, I will begin with the objectives before moving on to the background and theory. I will then briefly touch on the prior work before going to the test procedure, where we will touch on the sample preparation and mounting as shown off to the right. Then Addison will take over to discuss finite element analysis before moving on to results and conclusions. And this is the fun part, where we'll show you the outcome of us breaking things, shown on the right. He will then end with some recommendations for future work. The primary objective of our thesis is to investigate the effect of the heat-affected zone on the performance of a stiffened aluminum panel. We will accomplish this by testing stiffened panels while varying the weld parameter of each sample. The secondary objective of our thesis is to validate the use of finite element analysis for predicting the structural member failure. Our samples will be made out of aluminum alloys. Aluminum alloys come in multiple different classes, which are dependent on the alloying element. 5000 series and 6000 series aluminum are typically used for marine grade applications, so this will be our focus. And this is because of their corrosion resistance, weldability, and high strength to weight ratio. We will specifically be using 5086 for the stiffened panel. And might I add that 5000 series aluminum boasts a higher strength than 6000 series aluminum, making it the choice for most marine projects. So now that we've talked about the material, we need to address how it will be used. And this will be done by joining a plate and a stiffener to make a stiffened panel. The elements will be joined by welding, which is undoubtedly the most common way for joining metallic materials. So now you're probably sitting here wondering, why are we testing a stiffened panel? Why not just test the elements individually? And I have a simple answer for you. It's what mimics a ship structure, shown off to the right. As previously mentioned, the samples will be welded. There will be a weld joint between the stiffener and the plate. Welding describes the general process where the base metal melts and fuses with molten filler metal. We still have to decide what welding process we will use. On the screen right now, you can see a welder doing deck repairs on the littoral combat ship LCS, and this is MIG welded. We also decided to use MIG welding for our welding process, and this is for 2 reasons. Before I give you those, let's discuss what MIG welding is. MIG welding involves electric arc between the base metal and a consumable electrode. Simultaneously, wire is fed with inert gas. The rest of the process follows that of the general welding technique that I explained previously. We opted for MIG welding for 2 reasons, and that is because it followed the work that we based our thesis on, and we wanted to remain consistent as to reduce the number of variables that we were changing, and also it is widely accepted and used in aluminum fabrication. One of the reasons being for it being faster, as the wire is spool-fed versus hand-fed, such as tungsten inert gas welding, or MIG or TIG welding rather. The welding method directly affects the amount of heat required to make the joint, and the amount of heat input into the joint and the speed at which it is added is what affects the heat affected zone. Now that the purpose is understood, let's look at the application for our thesis. And what better way to do this than to compare a historic example with a modern example? On the left, we have the SS United States, which was constructed with an aluminum superstructure and broke the transatlantic speed record on our maiden voyage in 1951. And on the right, we have the independent variant of the littoral combat ship LCS, made entirely out of aluminum and constructed for the U.S. Navy. The flagship of the fleet, the USS Independence, set sail in 2008. While improvements have been made over the last half a century or so, and the cost of aluminum has gone down relative to its alternatives, there is still a need for study. As much as the picture on the right looks appealing and all, it can be a little deceiving. This entire fleet is suffering from cracks in both the welds and the bulk structure. which has compromised the ship structure and can lead to catastrophic failures. My intention with this comparison, if you will, is to show the evolution of aluminum in the marine industry, now shifting from the commercial to the military side. Additionally, it is to illustrate the need for future study. As much as the cracking seems like a massive issue, there are still reasons why welding is used, and this has a historic link. As I'm sure you're all aware, back in the 1900s, riveting was used for ship construction, as evident in this picture in the construction of the Titanic. Rivets create stress concentrations, which make ships more susceptible to catastrophic failures. And it wasn't until the 1930s that riveting became an obsolete practice and welding replaced it. Welding requires less time and money and produces less stress concentrations than riveting, making it the more appealing option for ship construction. Now, welding has even been automated, as shown in this picture of a Japanese shipyard. Switching gears into the theory, let's discuss what the heat-affected zone is, and it describes heat conducted throughout the material beyond the weld bead. The affected region demonstrates a significant change in material properties, and this is due to the microstructure being reset from the extreme heating and cooling cycles. This also results in a strength reduction. At this point, thermal diffusivity usually pops up into the conversation, which is the measure of thermal conductivity divided by density and specific heat capacity while remaining at constant pressure. In more layman's terms, it's the rate of heat transfer within a material. The size of the heat-affected zone is inversely related with thermal diffusivity. Therefore, higher thermal diffusivity yields a smaller heat-affected zone, as the heat can dissipate more quickly. But the high thermal diffusivity also means that the material requires more heat during the welding process. And this is where the comparison between steel and aluminum comes in. Aluminum has a high thermal diffusivity and therefore requires more heat during the welding process, making the heat-affected zone of greater concern during welding. The size of the zone is something that can be controlled. By maintaining a high weld rate, the heat has less time does not have a lot of time to diffuse, and therefore can be reduced. Eurocode 9 can be used to quantify the heat-affected zone, as it offers information on the extents, area, and properties in this region. For example, information is offered on the boundary of the heat-affected zone in terms of material thickness and weld method. Von Mises stress will be used during our finite element analysis, and the purpose of using this stress is to determine if a material will yield or fracture. If von Mises stress is equal or greater than the yield limit under simple tension, then the material will yield. It is often referred to as combined stress because there's lots of different stresses factored in, shown on the right. It is also a theoretical stress and allows for the comparison between general 3D stress and uniaxial yield stress limit. I might add that it's also nonlinear. Switching gears, let's now talk about the prior work done at Webb. We are the sixth thesis to use the structural test bed, a Southwark Emery universal testing machine. Taking a step back, in the nearly 70 years that Webb has had the test bed, shown on the right, there have only been 5, now 6 theses to use it. Even with its age, it has remained operational. However, that is not to say there weren't some experimental difficulties. The 2015 thesis, the most recent work, is the basis for our work, so let's see what they did. Gilfix and Guzera had tested 4 identical samples until failure. Their work and ours differs from the previous work done on the test bed, as ours are structural load tests versus simple tensile tests. The objective of their thesis was to examine how welding impacts the performance of a realistic marine structure. The specimen design is shown on the right and used a dog bone shaped plate with a T-stiffener welded on it. This was also donated by Metal Shark. Since they were the pioneers of this work, they had to design clamps that would interface with the test bed, which are shown off to the right. These are still available in Haverly and were utilized by Addison and I in our testing. Their testing did, however, yield some interesting results, which are attributed to the additional stresses acting within the material. Their 4 samples failed at the ends of the stiffener, pictured off to the right, as opposed at the narrow section of the dog bone. The stiffener is seen actually peeling off the plate, and the reason for this might be the biaxial loading, as the welds were not full penetration welds, and when strain is transferred from the stiffener to the plate, membrane stretches are induced and a bending moment is created. which is consistent with the shear at the end of a fixed beam. 9 years later, Addison and I opted to continue Gilfus and Guzera's work. To improve their test results, we opted to further develop the specimen geometry in order to make it fail at the desired location, the reduction in the narrow end of the dog bone sample. We focused on 3 different aspects of the stiffener geometry. First, the end shaped. From 2015 Thesis, they had a square end, shown off to the right, and we switched to a sniped end, also shown on the right. Additionally, we reduced the stiffener size, moving from 2 inches by 2 inches by 1/4 inch down to 1.5 by 1.5 by 3/16 inch. And last, we changed the stiffener alloy from 6061 to 5086, which came with the strength increase. Additionally, we focused on varying the weld parameters, whereas their 4 samples all had the same weld parameters. And lastly, we altered the strain measurement system, changing from strain gauges to digital image correlation, or the DIC system. We expect with these changes, we'll be able to achieve the stiffener breaking at the desired location. And this is a picture of the strain gauges and a picture of the DIC system. Regarding the experimental method, we asked Metal Shark to vary the heat input of each sample, which was achieved by varying the voltage and amperage set by the welder. Since we knew the weld speed and the weld length, which was consistent as the geometry did not change between each sample, we could calculate the time of the weld. And then we used this to calculate the heat, which is the voltage, current, and time all multiplied together. We would then measure the dependent variables, the force and the deformation, using the Instron equipment. We calculated our heat to range from 60.34 at the low end to more than double at 128.41 BTU. I will now move on to discussing the test procedure. The first step was to prepare the sample surface for DIC recognition, shown off to the right. There are 2 big takeaways that I want you to take away from this. First is that we need to have ample contrast between the sample surface and the markings. This was achieved by using a gray primer on the sample surface and then black markings. Second, the markings must not be uniform, as the DIC system tracks the movement of individual particles, or markings rather, over the length of the test. Once the sample was adequately prepared, we could then move on to mounting the sample, and this used the clamps that were designed by Gilfus and Guzera. I would like to note that this was a friction type connection rather than relying on the shear and the bolts to hold the plate up. After the sample was mounted, we could then run a check test to verify that the DIC system could pick up the sample surface, and this used the test bed shown on the right. We then ran our final test at 0.2 inches per minute until failure, and the video extensometer took pictures every 0.88 seconds, or 68 pictures were taken every minute. We could then move on to post-test processing using the DIC system. At this point, I'm now going to hand over the presentation to Addison to discuss FEA.
Thank you, Alex. Stepping away from the physical aspect and into the simulation side, 2 separate finite element analyses were to be performed as a part of this thesis: a preliminary analysis and a heat-affected zone prediction analysis. The goal of the preliminary analysis was to ensure that the sample would fail at the desired location, its center. And the goal of the heat-affected zone prediction analysis was to model the heat-affected zone based on weld parameter using the testing results. Before discussing the analyses, I'll provide some basic context on how the simulation model was set up in FEMAP, an industry-standard FEA program. Regarding the geometry of the model, the heat-affected zone dimensions were based on guidance from Eurocode 9. For 1/4 inch plate, the size is 1.18 inches, and for 3/16 plate, the size is 0.79 inches. The figure demonstrates how these dimensions are placed from the weld. Additionally, Eurocode 9 provides reduction factors for which the yield strength and ultimate strength are reduced in the heat-affected zone. They are as shown. For static analyses, the finite element method requires a fully fixed location to hold the model in place. This constraint is shown in red. In blue are the fixed constraints that allow only axial translation along the length of the model. These constraints were applied to the outer surfaces of the model. Even though the real model is clamped in the areas enveloped by these constraints, they are deemed adequate because, for one, the used constraints have a significantly larger cross-sectional area in comparison to the center of the sample. And two, we did not want to have a constraint very close to the end of the stiffener because that could affect the simulation's calculation of that stress concentration. For loading, a force was evenly distributed on the side that was free to translate. Solid elements were used for this analysis rather than shell elements for increased fidelity. Hexahedral and wedge elements are typically used together, as wedge elements fill in the gaps between hex elements as the geometry changes. Tetrahedral elements are used to model more complex regions. In creating the geometry in SOLIDWORKS, various solids were present that needed to be connected in the FEA. The connection type used are glued connections, where calculation is transmitted across the connection without the specific nodes of the elements needing to line up. Above, you can see the cross-section of one of the samples. The unaffected plate and the heat-affected plate were connected as shown. To connect the stiffener to the plate, this connection needed to be modeled through the weld. Since there was no edge prep on the sample, and it was not a full penetration weld, the stiffener and the plate were not actually connected, and this can be seen in the gap pointed out by the arrow. Finally, the heat-affected region of the stiffener was connected to the top flange of the stiffener. The plate and the lower part of the stiffener were modeled using hex and wedge elements, while the weld bead and the stiffener flange were modeled with the TET elements. Von Mises stress was analyzed as opposed to Tresca stress because Tresca stress tends to be more conservative, and we are prioritizing accuracy since we are testing to failure. Finally, nonlinear analyses were performed. FEA is typically done elastically in simpler cases, but a nonlinear analysis provided more depth. Nonlinear FEA is an iterative process as the elements deform as the load increases. First, the preliminary test was performed. This analysis was an elastoplastic analysis, and its bilinear nature can be seen above, with strain on the x-axis and stress on the y-axis. Instead of a complex material property curve, basic material properties are input, and the material yields along its Young's modulus, E, until its yield strength is reached, at which point it yields along its assumed plastic modulus, H, until the ultimate strength is met. The plastic modulus was assumed to be half of the elastic modulus for this study. The following results are for the sample being put to a loading of 60,000 pounds. I would like to make mention that the color scale can be a bit misleading if you don't know exactly what you're looking at. The stress in the heat-affected zone is significantly less than the stress on the unaffected base metal, hence the color difference. However, they are very similar in regards to percentage of ultimate strength. Therefore, they are both regions of significant interest. Overall, the analysis showed that the sample should fail at its center, as the stress at a representative element at point A was 29 KSI, while the stress at a representative element at point B was 22 KSI. The maximum stress was present in the unaffected base metal and was 39 KSI. Unfortunately, jumping back into the physical, our testing did not necessarily go as planned. The force measurements we obtained were inaccurate. Our testing was performed via extension rate rather than loading rate because of what we thought was an issue with the testing software. However, the force error turned out to be a physical error with the load cell. As you can see, the forces would plateau after an arbitrary load was reached. And above, you can see the comparison between the preliminary FEA and the test results. Therefore, the scope of the FEA needed adjustment. The preliminary analysis was unchanged, but two new analyses were added: an analysis using the 2015 geometry and an analysis using the updated 2024 geometry. The goal of the analysis using the 2015 geometry was to calibrate the material property stress strain curves to match up the FEA results with their previous thesis testing results. Then the calibrated material property curves would be used in the 2024 geometry to predict the performance of an average welded sample. For the 2015 FEA, their analysis needed to be improved upon. As you can see, the FEA results were not correlating close enough with the testing results to be considered predictive by our standards. Primarily, the heat-affected zone needed to be geometrically added to the model as it had for the 2024 sample, and different material properties needed to be used here. the stress strain curves needed to be manipulated in order to have the results calibrated. The method of accomplishing this involved maintaining the Young's modulus, yield strength, and ultimate strength as set forward by Eurocode 9. Only the points in between were manipulated. For only the 5086 curves were manipulated because our sample was entirely made of 5086, and additionally, the plate takes more load than the stiffener. For this nonlinear analysis, the sample was loaded to 75,000 pounds, as higher loadings would result in the sample failing, and 10 load steps were present. As can be seen, the FEA was successfully calibrated to their results. Their results are shown by the triangles, and our results are the squares. The model underpredicts strain slightly at lower loadings, but is much more accurate at higher loadings. The material properties of the 5086 aluminum alloy were then imported into a model using the 2024 geometry. This sample was loaded to 96,000 pounds, and again, 10 load steps were used. As you can see, the updated FEA showed similar results at lower loading to the preliminary analysis, but at higher loadings, the difference was clear. This was because the new model represented the plastic region much more accurately than the bilinear preliminary analysis. The results of this thesis are a combination of the physical and simulation. We were successful in each and every sample failing at its center. This is consistent with the results of the preliminary finite element analysis. As you can see from the picture, the failure at the plate is much smoother than that at the stiffener. This is because this implies that the failure initiated at the plate, and when that failed, stress was rapidly diffused into the stiffener until that failed as well. However, using extension as our main evaluation method, there was no clear correlation between extension and the stiffener, extension and heat input, our main weld parameter. The total extension of the sample may not and likely doesn't represent the force at failure, which could vary significantly. Additionally, the FEA cannot reasonably predict force on weld parameter since there is not enough data available. However, if the FEA is considered for an average sample, which failed at an average strain of 4.1%, which you can see on the y-axis, the associated interpolated force value is 94,000 pounds. This should be considered as an estimate for the loading at failure. Regarding the DIC system, it models only local strain, which is based on the calibrated area of the DIC camera. This region is about 8¼ inches tall. All other calculations in this thesis are based on bulk strain, which accounts for the total length of the sample. Since our sample geometry is irregular and changed cross-section, the DIC results could not be extrapolated to be compared to the bulk strain. Additionally, on the left, the black regions are those that are not calculated by the DIC software. I will now play the replay from the DIC system. Note for this 8-second video, the first half shows the elastic strain, and the second half shows the plastic strain. And I will play it again. As you can see, the pattern changes significantly from the first half to the second half. Areas of high strain appear in red bands during the plastic deformation. These angled regions of higher strain are known as shear bands. These occur because of the face-centered cubic crystalline structure present in aluminum. Bulk shear bands occur from critically resolved shear stress in these slip planes within the crystalline structure. Overall, the results of the DIC system showed an average of 15% local strain at failure. In conclusion, we improved the failure method of the sample through its physical alterations, including the stiffener material change to 5086, sniping the stiffener ends, and decreasing the stiffener size. Ultimately, we believe that the material change had little impact on the failure method, since the 2024 geometry FEA showed reduced stress at the stiffener ends in comparison to the 2015 calibration. The stiffener end geometry changing may have helped some, but the 40% drop in stiffener cross-sectional area likely had the greatest impact. However, the test results were not fully realized due to the force measurement issues. The 2015 sample failed too early. Our samples failed properly, but data was not measured properly due to the load cell issue. So the true performance of the sample is still unknown. The weld parameters were not fully investigated as a part of this thesis, but easily could be, assuming successful testing. Regarding the DIC results, only local strain could be measured. Local strain was useful in being able to view the presence of the shear bands, for example, but not in adding usable data points without the associated force values. The DIC would be more useful with a wider lens, which is purchasable, or if a smaller sample was used so the calibrated area did not exceed that of the sample size. Finally, a nonlinear FEA was successfully developed that was representative of the sample. Overall, we were able to meet our objective of developing an FEA model, but could not fully investigate the performance of the heat-affected zone. For recommendations for future work, performing testing with an operational load cell testbed would allow for the weld parameters to be investigated. Additionally, fatigue testing could be performed, which is more realistic of a ship's structure over its lifetime. Samples that are TIG welded rather than MIG welded require more heat, so the heat-affected zone performance in regards to weld method could be compared. And finally, the impact of the stiffener being 5086 rather than 6061 could be explored. Thank you all for listening to the two presentations. I will now play a video of our first sample failing. Keep in mind, it was much louder in person. All right. Thank you very much. I'd like to welcome Will, Miguel, and Alex back up for any questions you may have.